So lesson 39, right? That's where we're starting. When you go on Google Classroom, the first thing you'll see in the notes, right, for each section, I have it split up that way for you guys, is this. So you have a copy of you will have a copy of all of my typed up notes to kind of follow along with. So, because I don't want to write out every definition for you guys. So it'll be there for you to follow along with, okay? So that's kind of where we're starting. What we're doing in lesson 39 is we're going to look at the area under a curve, okay? And in calculus, we look at that a little bit differently because we have formulas for finding certain areas, okay? But it's going to be a little bit different when you have a curve, right? Because the curve is defined differently for each equation or each curve that we're talking about, okay? So it's not just a solid formula. So we're going to look at what that's going to do and how calculus will then allow us to find those areas, okay? So kind of just to start, right, looking at the beginning here, we use area, right, to describe the surface of items. How much is it gonna take to fill up that item, right? So like a table, a piece of paper, okay? We usually apply some sort of units to that because we measure them, right? So a table, the area is 1,450 square centimeters, right? Because the dimensions are measured. If you go around the length and the width, they're measured in centimeters, okay? For what we're looking at, we're going to use area to help us represent distance or work, right? That's a physics term, okay? And force, or the total force. So we're going to be able to connect this now using area to other subjects, okay? So I know in the beginning of math they always stress units. I stress units on problems, okay? That's something we can see. It's easy to see what 9 feet is. If we just say the number 9, sometimes people can't fully visualize what that is, okay? So we're going to strip away those units and just look at area as a real number that's going to describe an abstract quality, okay? With everyday closed figures. So it allows us to study the number associated with it without having to worry about the units that go along with it, okay? So we start with the basic formula for area of a rectangle. That's something we all know, okay? We know that the area of a rectangle is defined as the length of it times the width. Okay, that's for all rectangles, doesn't matter how big it is, right? So here's my rectangle. Then I'm going to find this as the length and width. Doesn't matter too much which one is length and width, okay? So we say this is L times W. But then we can take that rectangle and we can say, well, we know what diagonals are. So if I take my rectangle and I draw in a diagonal, I end up saying now that these two, because from geometry, we know that these two triangles end up being the same. So then I can say that the area of a triangle, and that's not working anymore, is going to be defined as half the area of the rectangle, right? So area of a triangle is half the area of a rectangle. Well, triangle, 1/2 length times width, okay? Sometimes we say base times height, but really it's like you took that triangle, made 2 of them, and then have formed your rectangle, okay? So that's how we get the area of a triangle. These are formulas we know, okay? You can also take a rectangle and create a trapezoid with it. Okay? Trapezoid says you have two sides parallel, two sides not parallel. Okay? So, actually, we're going to look more at a parallelogram. Okay? So, if I put in here, then we can get the area of a trapezoid is going to be half the sum of the two bases times the height. Okay, these are formulas we all end up knowing, and you most probably prove them in geometry. Okay, so things we know. We also can say that the area of a circle, right? Here's our circle. The radius goes from the center to a point, and the area here is pi times the radius squared. Okay, these are all closed geometric shapes: circle, rectangle, triangle, trapezoid. Okay, but we haven't exactly defined how to find the area of a region that's bound by a curve. Okay, so we start trying to figure it out by considering a graph that is continuous. That means there are no holes, no jumps, no breaks, okay? So it's like when you draw the curve, your pencil starts and it doesn't get lifted before the curve ends. That's what continuous is. Everywhere increasing, right? So it means that points on the left are lower than points on the right, okay? Because it means it's constantly, the y values are constantly getting bigger. And they're not negative on the interval. We say the interval is AB. Okay, that just means that between these x values, between the two x values here, your graph does not go below the x axis. Okay, your y values are positive on this interval that we're looking at. Okay, then we're going to consider the area that's bound by the graph itself, the x-axis, and this interval. So here's the curve, okay? So this is one boundary. Here's our x equals a and x equals b. And then the x-axis. So we're talking about this area here, bound by the curve, x equals a, x equals b, and the x-axis. So we're going to call that the area under the curve on the interval AB. And that's what it looks like, okay? So to kind of begin on how we're going to find that, right? We don't know how to do that because it's not a shape we know, because this is not a straight line, it's a curve, okay? So we begin by saying if I have a rectangle here, let's say the dimensions of it are 8 by 4. Then you could tell me that the area of this rectangle A is 32, okay? Then, looking at this curve, we're going to say this is A. So A lies under the function f, above the x-axis, and between x values A and B. Right? But what is this value of A? Okay? So we start by saying, well, can we prove that such a number A exists, right? Can't define it if it doesn't exist. So if it exists, can we develop a way that allows us to find the exact or the precise value of A? Okay? And that's what we're going to do in this lesson, is find a definition, okay, like limits or derivatives. Find a definition that allows us to find this value as long as it exists. Okay? So, how are we going to do that, right? We start by finding an approximate. So, an estimate, right? Maybe not exactly yet, but an estimate, an approximation, okay? By drawing rectangles and then adding the area of the rectangles together, okay? So, we're going to start to see how it's done by using a curve that we know. So we're going to start with a graph of y equals x squared plus 1, okay? That's above the x-axis and between x values 0 and 2, okay? So first, what does that graph look like? All right, well, when x is 0, y is 1, because 0 squared plus 1 is 0. And when x is 2, y would be 5, because 2 squared is 4, 4 plus 1 is 5. Okay, so then I'm going to make this graph. So above the x-axis, here's my x-axis. When x is 0, y is 1. And when x is 2, y is 5. We know it's x squared, so we know this is not a straight line between these two. Okay? We know it's a curve, so we know it looks like this. Okay? You could even figure out when x is 1, that y is 2. So maybe let's space this out a little bit more so we can see it clearer as a curve. So more like this, okay? But we're just worried about between these two values. So I'm going to draw in a line here, here, and then we're saying above the x-axis and the curve. So this is what we're looking at, okay? So it's the area that's shaded here, right? That's what we want. But again, it's a curve, so how do we do that? Okay? So first, we're going to take this and we're going to divide the distance between your x values into 4 equal intervals, right? So from 0 to 2 into 4 equal intervals. So you're dividing your x values into equal parts, okay? Well, that's 1, 2. So each one we're talking about being a width of 0.5, okay? So here's 0.5, then at 1, 1.5, and 2, okay? So here's 1. Let me do this so we can see the bars. Okay, so here's 1 interval, 2 intervals, 3 intervals, and then our 4th, okay? So we divided our interval, 0 to 2, okay, into non-overlapping parts. We're going to take them and we're going to draw vertical lines from the end of each partition to the graph of the function, like we did here, okay? Oh, and you can't see the graph. There's the graph I've been talking about, okay? So from the end of each partition to the the graph itself, right? Or to the curve. Okay, so we did that. Now you're going to draw rectangles, because these aren't quite rectangles, right? Because this is a curve. It is not a straight line. So we know how to find the area of a rectangle. So we're dividing these partitions, or these areas, into something we do know. Okay? So it depends on if we're going to do a left hand or a right hand rectangle. Okay? So we're going to start with the left side of each partition is used as the height. So the left side, okay? So this is one partition, 2, 3, and 4, okay? So we're using the left to be our height. So for here, right, this is our curve. This is the height of our rectangle. So we have this rectangle here. Then for this next one, this is our height. So we get this rectangle. Okay, the left hand partition, so height, and then height. Okay, and you have to figure out the y coordinate. So the left hand partition, when x is 0, we're here at 0, 1. Then at 0.5, you're at 0.5, 1.25. Then here, you're at 1, 2. And here, you're at 1.5, 3.25. And then we know this is 2.5. But it's not really part of our partition because the left-hand side here, there's no curve that we're finding the area to the right of it. Okay? And then when we look at it, we see that all of these rectangles are falling below the curve. So we have all of this missing area if we just find the area of these rectangles and add them together. We're missing this area, this piece, this, and this. Okay? If I were to go back, though, and draw my rectangles using the right-hand side as our height, okay, now the height here would come above my curve. Then if I go here, again, these are coming above the curve. So you have all this overlap that's extra when we draw the right-hand limit. Or not the limit, I'm sorry. The right-hand partition, the rectangles using that height. So we end up having this extra, extra, and extra. Okay? But if you look closely, the extra on the right bars ends up being the missing part of the left-hand rectangles. So this piece that's extra here equals this piece that was missing from the others. This extra is the missing piece. This extra is the missing piece. Okay? So if we then look at it, we can see that the sum of the areas of the 4 rectangles that we first draw, so on the left, right, so if you look at your notes now, it's a little clearer here. Okay, so we look at the sum of the areas of these four rectangles. It's called a lower sum because that's telling us that the area under the curve has to be less, or that area is less than the area of the curve. And the sum of the areas of the 4 rectangles on the right is called the upper sum. Because the area under the curve can't be more than that. Okay, so the lower sum is the left rectangles. So we're going to say that that is the ones that we started with, right? So the area of this first one would be the height of 1 times 0.5. So the function evaluated at 0 times the width of the interval plus the function evaluated at 1 times the width of its interval. Function evaluated, or not at 1, I'm sorry, at 0.5 because we need all of our rectangles. Then the function at 1 times its width plus the fourth one would be the function evaluated at 1.5 because we're using those left-hand rectangles. So the lower sum ends up being 3.75. Okay, the upper sum is using the right rectangles. So that's the part that's hanging over, okay? So that's going to be, this first rectangle's height is now here because it's going to the right-hand partition. So it's the function evaluated at 0.5 times 0.5 because that's how the interval we divided up was a width of 0.5 because we divided it into 4 intervals. Then the next one here is the function evaluated at 1 times 0.5 plus the function evaluated at 1.5 times 0.5. And the last one, the height here, is 2. So the function evaluated at 2 times 0.5. So then the upper sum ends up being 5.75. We're just finding the area of the rectangles that we created to help us approximate the area under the curve. We know that this lower sum, right, these 4 rectangles, ends up being smaller than the area because we have this missing part. And then the upper is more than the area because we've got this, we've covered the area under the curve, but then we have our additional part. Okay? So, tells us that the area then under the curve, we define as A, is somewhere between 3.75 and 5.75. Because these covered less than these rectangles, these covered more than. So to generalize out, we can say that the lower sum is less than the area, and that's less than the upper sum. Okay? I can tell you that this exact value that we're trying to find is 4 2/3. Not quite there yet, okay? It's coming later on in later lessons. All right. Just, you take your interval, you divide it into the correct partitions that they're asking you to, and then you draw a rectangle, you draw your intervals here, and then the lower sum, think of it as left, right? The rectangle gets drawn to the curve at the left partition. The upper sum, the rectangles are being drawn from the right partition. Okay. All right. So the error in this lower sum, okay, is the sum of the 4 triangular regions. So we can see that it's a mistake, or it's less than it by the sum of these 4. And the error in the upper sum is going to be the sum of these 4 triangular areas that are above the curve. Okay? If you were to take your partition, so your x interval, and divide it into smaller segments, so say 8 rectangles instead of 4, your approximation for the area is going to become closer to the actual area because the rectangles are getting smaller, they're getting closer together, so these heights are getting closer together, so the missing or the overlap becomes less. Okay, so you need to keep that in mind when we're looking at these approximations. Again, this is approximate. You can't tell me exactly what it is yet. Okay. So just to walk through one more example, okay? Let's say we're going to use the same curve. So y equals x squared plus 1 we want the lower sum on the interval 0 to 4. Okay? Divided into 4 sub-intervals. So to do this, right, first you begin by sketching your curve. So I'm going to graph this curve, but only worry about the interval that you're looking at. We don't really care what's happening beyond that. Okay, so when x is 0, y is 1. And then 4 intervals. Okay, so I'm taking 0 to 4, and I'm dividing it into 4 equal parts. So it's going to be at 0, 1, 2, 3. And then 4 is where it ends. So when x is 0, y is 1. When x is 1, y is 2, 2, 5, 3, 10, and 4, 25. No, 17. Because 9 plus 1, 4 plus 1, and 16 plus 1. For your graphs, use graph paper. Okay, it's going to make it easier. 2. Okay, so here is my curve. Okay, and then all the way down to 4. So 1, 2, 3, 4. And this is 17. Fairly large graph. Okay, so the lower sum, right, means that your rectangles are drawn from the left. So 4 rectangles, they're each one x value thick. Okay, so from the left, I'm starting here, I go up to 1, and that's my first rectangle. Height of 1, width of 1. Okay, so the sum of the lower rectangles, it's going to be the function evaluated at 0 plus, or not plus, times the width, right? Because the height is on the curve. And the width of these bars are 1, because 4 divided by 4. 4 is the length, and you're dividing into 4 intervals, okay? Plus this next one. So you go up to the curve here. So this is going to be the function evaluated at 1 for the height times the width of the bar, which is 1. Then your third rectangle. Left hand, go up to your curve. So it's the function at 2 times its width would be 1. Plus the last rectangle, you go up to the curve at 3 and then across. So the function evaluated at 3 times its width. Okay. All right. So that would be 1 times 1 plus 2 times 1 plus 5 times 1 plus 10 times 1. So 1 plus 2 plus 5 plus 10. And that's the area of these rectangles that were drawn for the left hand of the partition. So that's going to be 18 square units. If you wanted the right hand, the height would still be the same. It would be at the curve, but we would use 4, 3, 2, and 1 because they have to go above the curve for the upper limit. So the green ones would be our upper limit if that's what we were finding. So we are approximating them using the left hand endpoints for the left hand sum or the lower sum, and then the right hand partitions would be the right hand limits or the right hand sums or the upper sums.